Hi everyone, myself Alan, and today we are going to bridge the gap between theory and practice by walking through a Python script that performs clear decomposition using the Gram-Schmidt process. Our goal is to understand how this code takes a matrix A and breaks it down into orthogonal matrix Q and an upper triangle matrix R. First off, what is QR decomposition? QR decomposition is a fundamental technique to factorize a matrix A into a product of two specific matrices Q and R. This factorization is represented by the equation A equal to QR. What is the matrix Q? Q is an orthogonal matrix. This means it consists of columns of orthonormal vectors where each vector has a length of 1 and is perpendicular to the orthogonal to all the column vectors. Mathematically, Q transpose Q equals I. What is matrix R? R is an upper triangle matrix. In an upper triangle matrix, all elements below the main diagonal are 0. This structure makes it very useful for solving system of linear equations. Now introducing the Gram-Schmidt process for QR decomposition. The Gram-Schmidt process is an engine that drives the construction of orthogonal matrix Q. It is a sequential method for converting any set of linearly independent vectors into orthonormal set. Our objective is to transform the columns vector of matrix A into an equivalent set of orthonormal vectors which will be in the form of columns of matrix Q. First, we have to start with the vectors A1, A2 and A3 etc. and end with orthonormal vectors Q1, Q2, Q3 etc. Now, let's take a look at this Python code. The function QR decomposition starts by importing the NumPy library, which is essential for numerical operations in Python. Inside the function, it first gets dimension of our input A, then it initializes three matrices. Q, an empty matrix that will hold our final orthogonal matrix. U, a temporary matrix to store our vectors after we make them orthogonal, but before we must normalize them. R, a matrix of zeros that will become our final upper triangle matrix. The first column, which is our starting point, we have to take the very first column of A, which the code calls A is to 0, and that becomes our first orthogonal vector U is to 0. Then to make it orthonormal, we just need to make its length to equal to. This code does this by dividing the vector by its own length or its norm. The result is the first column of our final Q matrix. Simple. Now for the core of the algorithm, this for loop is where Gram-Schmidt process really happens. It iterates to the rest of the columns A to build the remaining columns of Q. First, A is to I and Q is to J is a dot product. It calculates the shadow or projection of our current vector form A onto Q vector which we already finalized. It then subtracts the shadow from our current vector. This inner loop does all the Q vectors we have built so far. By removing all the components that lie along the previous vectors, what left is guaranteed to be orthogonal or perpendicular to all of them. Finally, just like before, the line Q is to I, which is equal to U is to I divided by np.linearalgebra.norm U is to I. Normalizes this new orthogonal vector to have a length of 1. It becomes the next column of our Q matrix. And in this for loop, we have used the Gram-Schmidt to build our Q matrix. The last piece is the R. This is very simple. This code calculates each element of R. We know from the math R equal to Q transpose A. This line of code is the direct implementation of the formula. The value R of I, J is found by taking the dot product of the jth column of the original matrix A and the ith column of the U matrix Q. The loops are structured from J equal to I onwards, which the R is an upper triangle matrix, meaning all values below the zeros are diagonal are 0. And the code first meticulously builds the orthonormal matrix Q column by column, then uses Q to quickly complete the upper triangle matrix R, successfully decomposing A into QR. Thank you.